Time. Good. So T stands for time, which means if time starts at a certain point, are we going to have the entire path when it graphs? Maybe not. Our path can sometimes be cut off. So like yesterday, what was the example I was doing with the thing that was hurtling through the air? The water balloon, good. And the big old sling and then someone pulling it back. So the water balloon launcher, right? The water balloon did not come up from the core of the earth and burst through the ground and fly and then go back down to the core of the earth, right? Unless, well, that's some water balloon. That's some water balloon. Anyway, so coming back. Made of cement and something a whole lot stronger. Anyway, so long story short, the water balloon did not technically go over that whole parabolic graph. So therefore, parametric mode's like, don't worry, I got this. It started here and ended there. So when we graph in parametric, we can have this whole time component. Oh, but the window was gross. We had to still kind of zoom the X's and Y's to see the whole path and all that jazz. I think, what was it, like 100 or something the X's had to be? 100, 150, something like that. We were trying to figure out when this thing would hit the ground. And to figure out when this thing would hit the ground, we played with our calculator a lot, and that was super annoying. And we're like, wait a minute. When it hits the ground, what's the y equal? Oh, so we could have just set y equal to 0 and solved. It was so much easier. But then we were like, wait, time out. Okay, so we played with our calculator, got a feel for parametric. It has a time beginning and a time ending. Wait. Do you remember that one other weird thing we had to be careful of? Time step. Remember how we had the right T max in there, but we still couldn't see it hit the ground, and we were like, what? And the problem was the step was too big. So it got all the way up until it almost hit the ground, and then the calculator's like, oh, I can't take another step because you told me to stop. So then what did we do with our step? I looked really foolish doing it yesterday. What with our step?
Oh, you did the smaller step.
Yeah, what was I doing? I made smaller steps. So instead of 0.1, it was 0.01. And did you guys also realize the calculator took forever to graph that? Why? Because it was doing all the steps for us. Thankfully, it was doing it and we weren't doing it, but okay. So that was all the stuff about the calculator and the window and all that jazz. Then we said, all right, let's talk about these parametric things. Let's talk about doing it by hand. By hand, we have to remember x has its own equation, y has its own equation. Since parametric equations are new to us, we can make this table by hand to get a feel for it. We don't have to necessarily, it's not like the beginning of the year where we studied really hard the linears and the quadratics and the cubics and the quintics and the polynomials and the rationals and the exponentials and the radicals and the so many different functions and their pictures and their domains, their ranges, their special characteristics, increasing, decreasing. We're not going to look at a parametric pair of equations and be like, I know what that is. No. We're only doing one section. We're just introducing it. So we're not going to have that kind of knowledge of them, so we're going to use tables. And the one weird thing with the table is that there's going to be an extra row or an extra variable, t's, not just x's and y's. But as we put in the t's, as we allow time to pass, we'll get x's and y's that we can graph. Just like normal, the x's and y's. The t's don't show up in the graph at all. The t's just say, he's legal, graph him. He's legal, graph him. And what I mean by legal is, that's a position that was actually true. Cool, put him down. That's a position that's actually true. Put him down. And as we graph, we're going to connect in order of time increasing. It's the only direction time goes. And we have to show orientation. Now, do you guys remember how we showed orientation yesterday? Orientation was something moving on a path. It's okay. Look in your notes. You should have done it 2 different times. Yeah. Well, there's the table, and then we connected the points. And what else did we put on the graph that's new? T's like made it. Look at the graph itself. Arrows. The arrows showing the direction of movement. So, what's a snazzy word for an arrow showing the direction of movement? Orientation. An arrow showing the direction of movement, that's going to be orientation. So, yesterday when we graphed, oh, go back. I tried. When we showed this one, see how there were arrows in the parametric, but there weren't arrows in the original? So this water balloon was flying from the left to the right, but if it was maybe the other team ricocheting back, they'd be flying the other direction. So depending on how the points are connected, it could be flying this direction or the other direction. And same thing with this one that we did. We did this guy, and we had to show the arrows showing what direction of movement, because in a different pair of equations, it could have been going the other direction. So we have this new thing called orientation also. So that was how to graph parametric equations by hand. We need t's. We plug in t's to the x and to the y. We graph those x's, y's, and then we, as we connect them, show the orientation, show the movement. Are we tracking? Okay. Then, the next big idea was, well, tables are nice. They're all right. But maybe it'd be nice every now and then to get to ignore the t, ignore the time, and just think about the path, because we're so much better at things in function mode. So maybe there will be a place of converting from parametric to function, from parametric to function mode. And so basically, I mean, you could put in parentheses conversion. Like, this is converting. It's converting from parametric to rectangular. And we're going to also do a little bit of converting backwards today. But the backwards is actually way easy. This is the harder one. But there are basically two steps. And step one says take the x equation, because every parametric pair of equations, there are two of them, one x equation, one y equation. Take the x equation, solve for t. Then take that t, plug in to the y of t. That's how you get rid of them. That's how you take them out. Eliminate. Think a sniper, we're sniping the t, but we can't just kill him. We have to do it legally, so we have to go ahead and isolate him. Ooh, we could go really deep on this analogy, but we won't. We can isolate him, right? When we isolate t, then we can go ahead and plug into y. He's going to disappear. He's going to be substituted out. And then we're going to have our final equation, which is the path. Now, remember, when we get rid of t, all the timing is gone. The direction of movement is gone. The how fast it's going is gone. The beginning and ending, depending on t equals 0 and t equals whatever. That's all gone, but we do know the path. We do know the path. And our brain can see this a little bit easier because it's like, well, 16x squared. All right, you're all having too much fun with the sniping of the t. Come back. So I have my 0, 0. I would have my 116. I would have my negative 116. I would know my path. Now, if I wanted to know where something was on this path after t equals 1 or t equals 2 or t equals 3, we would need to go back to parametric. But for the path itself, there it is. Now, I wouldn't put arrows on it just because parametric would show orientation, and I don't know, without plugging in the t's and making a table, I don't know if it's going this way or if it's going that way. But to eliminate the t means, hey, you got the t's in there, you have parametric, let's convert back to function. And that's what we did on this example. He was just a little bit harder, algebraically, like the algebra was harder. But we still isolated t. Haha, we got him alone. That sounds creepy. And we took it. And we went ahead and plugged into the y equation. We said, now we're taking him out. It's like erasing his identity. Like, whoop, hey, you're gone. And then all of a sudden we have all these in terms of x. We did a little bit of manipulation. I think, Jacob, you were asking me some of these things. Different ways of doing it. So you could have multiplied by the reciprocal, or you could have done my snazzy trick of multiplying top and bottom by the common denominator. Or you could have done what Jacob was kind of seeing, the heart method. You would just have to do it 2 separate times, that division 2 times. Either way, you end up at y equals, oh, we didn't even look at it yesterday, guys, but this is the path. Is y equals 1 minus x squared a hard graph to make? Not really, because it's a parabola. If you think old school, it's a parabola that's been, right, flipped down because there's a negative on the outside, and what else happened to it? Up 1. Because you would think negative x squared plus 1. So you can think that it's been flipped and up 1, or you could think of it's been down 1 and then, down 1 and then, yeah, and then flipped. Ugh. Both ways work, but you just have to do the right order. Okay, so we are ready to, guys. What's going on? Well, okay. Question. Do we like seeing thetas all of a sudden? Okay, so here's one thing that we could do. We could actually go ahead and say x is equal, because this is what you'd have to do in your calculator, right? You'd have to put a t. It's not cost, it's cosine of t. We could go ahead and substitute in a t. That's not bad, that's not wrong. We could substitute in a t. So sometimes they might give you parametric equations that have betas. No big deal. I mean, we've put equations in our calculators that don't have x's, and we have to make them x's because we don't have any options. So that's all right. We can make the thetas into t's, no big deal. But they say to eliminate, take out the parameter. But the bummer is, to take them out, don't we have to get them alone first? Yes. Okay, we'll look at the steps. Where do we normally try to get them alone? In the x or in the y? Yeah. Get them alone in the x, and then you can take what's left and then use it to erase his identity in y. So, does this look fun to getting t by itself? Well, that's a good like brownie point answer, but I don't even think that. If you divide by 2, it's closer. But what's still the problem? Where's t? Times cost. No, that's not a thing. In cosine, right? He's not times cost, he's in cosine. Well, how do I get rid of cosine? Ah, inverse cosine. Look at you guys pulling out your arsenal. So, now what do we have to do with it? Now that we've gotten t isolated, we've got him alone. Now I have to take this and plug him into... Now, is this wrong? And the answer is no, it's actually quite right. But, doesn't it look absolutely disgusting? I thought this was supposed to make things better. I thought this was supposed to make it to where we could see the path clearer because it's supposed to relate to stuff that we've been doing all year. Who the heck is 3 sine or cosine inverse of x over 2? There is a way to do this. It would be a little crazy. It would be taking what we know about trig and saying things like, inside inverses go ratios. And so ratios, so katoa, I could make this little right triangle off to the side and be like, well, for some triangle, I must have an adjacent that's x and a hypotenuse that's 2. So cosine inverse, this is a cosine. We could use Pythagorean theorem, c squared minus b squared is a squared square rooted, and make this guy into a 4 minus x squared. And we would do that because we're supposed to be finding sine of this nasty guy, and so it really would be 3, sine would be opposite over hypotenuse, and you're like, well, I'm not sure that's really much better. We're going to come back to this in just one second. Can I show you another way whenever you have sines or cosines to eliminate the parameter that gets us straight to a nice answer we should recognize instead of to a weird one that we don't recognize? Okay, remember this equation. We're going to make a new page real quick. Let's try again. But let's try again using, I'm going to go straight to the cosine of t and straight to the sine of t. Are my numbers in the right spot? 2 and then 3? Is that right? Okay. I'm going to review something with you. Remember back, I know, some of you guys missed trig, it's been a while. Remember back when we were doing trig, right towards the end, we were doing t-proofs and solving equations and having to access all of these equations, Pythagoreans and double angles and half angles and quotients and reciprocals and, okay. What was the easiest Pythagorean property using sine and cosines? No, Pythagorean. A squared plus b squared is c squared. Wait, squareds. Squareds. Cosine, sine squared plus cosine squared is what? Okay. I'm going to actually do it the other order, if that's okay. Do you guys agree this was a thing? Yes. Okay, if it was a thing, it still is a thing. So it's still a formula. We just haven't used it in a long time. What does this formula do? It says, give me cosines, give me sines, and if I can put it all together like this, I'll say it's 1. How is this going to help us take out t? How could I solve for cosine? What would just cosine be? What would just sine be? What does this formula tell me I can do? Take a cosine, take a sine. Where's the t? Gone. Cosine squared plus sine squared is 1, so therefore I'm able to go over here and say, well, who is cosine? That guy. Who is sine? That guy. Sweet. Plug it in. Ha! T's gone. And what do I have left? X squared over 4 plus y squared over 9 equals, should we recognize him? He's an ellipse with a minor radius of 2 horizontally and a major radius of 3. It's been like 2 days. You're already forgetting it all? Lame sauce. But pause. How on earth does that make any sense with this grossness that was going on the page before? That's not an ellipse, is it? Couldn't I play with him a little bit? When I play with him a little bit? Jacob, remember from yesterday how we said that you can do this division as long as you do it 2 times, right? Oh, I don't know why I divided by x. It's 4 over 4. Couldn't I add that to the other side? What's 4 over 4? Ah, you're welcome. So could you do it that way? Yes. But what would you need to remember? Child's play, huh, Jordan? What would you need to remember? Well, what an inverse does. So adjacent over hypotenuse. To finish with Pythagorean theorem, what a sine does, opposite over hypotenuse, and how to algebraically manipulate to try to figure out who this guy really is. Oh, it's an ellipse, haha, with the minor. Anyway, does this look easier? I think so, but what's the linchpin? What's the key? What's the weapon that you have to bust out in order to do this one? Pythagorean identity. Cosine squared plus sine squared is 1. If you get cosine and you get sine, you can plug into the identity and say, poof, t is gone. It's a little magical. It's quite a nice weapon to use, but you have to remember that you have it and how to use it. Ooh, looks like some life lessons going on here. Anyway, can I give you one more interesting trig one? I could give you another sine cosine one, but we already did one of those. What if I was to give you something like, this? Let's see if you guys can figure this one out. Using similar logic to what we just did. There's another weapon. It's a little bit different, but it works very, very similarly. You might have to review and find somebody in your group that has a textbook that can go back and look at all those properties. What if I were to give you x equals 2 plus 3 secant of t, and y equals, give me a second, 1 plus 4 tangent of t. Oh, Lainey just busted out the weapon if the rest of you guys can figure out what it was. Chapter 6 or 5, somewhere in there we were talking about. Chapter 5? 5-1? Nice. Go find your weapon. Something with secants and tangents, something with maybe squareds. See if your group can do it. You guys start with your weapon, then do some plugging and chugging. See if you can follow the last example. Can you use the weapon to take them out? All right, what's the weapon?
If you want to change the square, use secant squared. Or we'll tangent t.
So what'd you have to do? Get the tangent alone. How would you get the tangent alone? That's okay, algebra. To get to here, don't we have to first and then divide by?
Yes.
So as soon as we have pluses or minuses, I think the center is going to be somewhere other than 0, 0. Wait, center. It's like I'm talking about conic sections again. Coming back. How do you find secant? Subtract, good. And then divide. So can't I plug in? Who's this guy? We're not used to seeing him like that. What would we do to get him in a nice proper form? Could we subtract? It'd be a minus. So why are people saying hyperbola? It's not plus, it's not an ellipse, but it is a hyperbola. With a center at 2, 1, and the vertices would be 3 apart. It'd be one of the sideways ones, right? 3 and 3 away from the center. The foci, oh, well, we could find it if we needed to. Forget that. C squared equals A squared plus B squared. The asymptotes would be plus or minus 4 over 3 because of rise over run. Anyway, yeah, he's a hyperbola. Wouldn't that be a lot nicer than thinking of x minus 2 over 3 secant inverse being plugged into a tangent? Ugh. Those Pythagorean identities are quite the tools, quite the weapons to pull out if you're trying to eliminate t's of parametric equations. All right, that was pretty spiffy. I think there's one more. One more topic, and it's a lot easier than what you were just doing. So we've gone from parametric x's and y's to eliminating the parameter, taking out t, to function. Now let's go the other direction. What if we have rectangular, or we could think of function mode? Let's say we had the path, and they want us to put in some timing. They want us to put in a t. So we're trying to go from function mode, from y equals f of x, to parametric mode, to the x of t, y of t. Now here's the dilemma. Well, t is gone here. There is no t. So if t's been erased, you can't just magically bring it back in unless they tell you something about it. So they're going to have to tell you something about your t. Let's put it this way. If t was totally taken out, not only killed or supposedly killed, but also erased as an identity, erased as in people's memories wiped, what's the only way that you could bring him back? You got to remember. You got to be given information about t. Otherwise, how else can you bring him back? He's gone. So you have to be given information. Sounds a little bit like born identity now. But anyway, coming back. If he's been eliminated, if he's been taken out, the only way to bring him back is to be given information about. Well, I'm kind of going with the whole, he wasn't actually killed, he was just disappeared and then came back. But that's like the born identity. He just like disappeared and showed up somewhere, and they were like, "Who's this?" The memories have been wiped. You're like, "Who are we looking for? Who's that?" It's kind of sad. It is a crisis, but look, t's back. It's okay. So y equals 1 minus x squared. There is no t. There is no t. Here's the path. But in order for them to want us to bring back t, to bring in some timing, they have to tell us the clue. So look at letter A. I'm using an example to kind of teach it and show you the process. But if you want the steps, step 1 would technically be to make an equation for x of t. Remember, for parametric equations, we're supposed to have an x and we're supposed to have a y. So as we're thinking about our parametric equations, x equals, y equals, the first thing we do is look at the clue and say, hey, can we make x? Well, guys, what's the clue in A? So if t equals x, what does x equal? Exactly. No, seriously, right? If t equals x and x equals t, we already have 1/2 of our pair of equations. Now, hold on. For letter B, maybe it's not quite so easy. For letter B, how are we going to start this process off? This one was easy. How do we get x equals? Okay, x equals t. But this one, how do we get x equals? Don't we have to isolate x? They might be like, uh-oh, we're going to take him out? No, we're not going to take out x. But can't we take our clue? And can't we maybe do some rearranging a little bit? Yeah? So then x plus t equals 1. Couldn't I subtract t from both sides? So then what's x going to equal? So sometimes it's as easy as just like, oh, I see x. It's obvious. Right there, x equals t. But sometimes you're going to have to rearrange just a little bit to get x by itself. Okay. So step number 1, make an equation for your x of t. Step number 2, substitute, there we go. Substitute x of t for x in y equals f of x. Once we know what x equals, hey, go look at your y equals f of x. Go look at your path and plug in x of t for the old x. Because wasn't there a place for x to go? So plug in. So y equals 1 minus who squared? Oh, well that's easy. 1 minus t squared. Dun, 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 dun. There's that parametric pair of equations. This one, the timing is a little different. This one, t is a little different, so it makes sense they'll look a little different. We have x already. What are we going to do with y? With y? Man. Yeah. So y is going to equal 1 minus x, who is 1 minus t, squared. My throat got dry, I'm sorry. Could we simplify this? Yeah, we'd have to FOIL. Don't kill a puppy. So when we FOIL, 1 times 1 is 1, 1 minus 1 is 0. We have negative 1t times, or plus negative 1t is negative 2t, times a negative will be positive 2t. Then we're going to have negative t times negative t is positive t squared times a negative. Long story short, after foiling and combining like terms, that y will turn into that y. And dun, 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 parametric equations done. You guys have your 2 steps? If t has been eliminated, they have to give us information about t so we can get them plugged back in. And we just kind of do the process backwards. We say, okay, fine. Given this clue about t, who would x have been? Okay, cool, let's plug in 4x, and now we have both x and y in parametric form. With that, kiddos. Dun, 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 dun. Okay, people who did or started, I should say, started homework last night. Do you have a place in homework that you want us to jump to and me to help preemptive strike sort of way to help those who have not yet gotten there in homework? Any tricky places? Any confusing places? Any hard problems? Bummer, man. No preemptive striking, huh? All right, if you want to write down homework, you can write it down quickly, but we have to go start 10-7. Because that means we're going to have more questions on Monday since we didn't get to start ahead on homework. So we got to get into 10-7 today. If you want to write down homework, it'll be up here for another like 20 seconds. Maybe maybe 15. Maybe now 10. Maybe now 5. Maybe now 4. 3 and 2. All right, 10.7. Calculators out, change your modes. Calculators out, change your modes. Oh, those are homework problems. There we go. Change your modes to polar, P-O-L. Change your modes to polar. Remember, 10.6 was just a big old introduction to parametric. Well, it wasn't that big, I don't think, but an introduction to parametric, and 10.7, a parametric. Not a parametric, an introduction to polar. Change your modes to polar. I want you guys to go ahead, change your mode to polar. Once you change your mode to polar, I want you to go play around in your y equals just a little bit. And I want you to see if you can get a good picture of what do I want to put in here? Let's do 5 sine of 3 theta over 2. I'm giving you a harder equation just because it's going to make you play with your calculator a little bit more. Yeah. There you go. Play with your window. Maybe start in Zoom Standard. Maybe change it up a little bit. Jacob, go ahead. Oh, I bet you have. If you guys can't do the fraction in the y, oh, no you don't. Your inequals might be turned on. That would mess things up. Is that better? Oh, now you're good. If your fractiony thing isn't working, go to apps and go to inequals and turn it off or quit it. If your fraction bar isn't working in your y equals, you're going to have to go to apps and then inequals. You must have turned on the inequalities at some point. You're going to want to quit that. Otherwise, you can't do the fractiony thing. You guys want me to show you how nasty this can be if your window's not set up right? Yeah. Okay. I'm purposely making my window bad just for an FYI. Okay, you ready? Let me go down Zoom Standard. Hold on. Okay, this is probably going to look like none of yours. And let's see if it works.
What's your window at Zoom Standard?
What is that, and how do I get that on my
What happened? It's a black hole. It's a turtle. I don't know. Anyway, what is it? What happened? Okay, let me zoom in. Maybe. It's okay. In honors of Star Wars. Star Wars. Oh, no. I don't want that. Hold on, I don't want that. Let's do Zoom Standard. Now, I made this on purpose bad. Oh, I made it pretty again. Lame. This is what you guys should have gotten if you did it correctly. Now, you don't even necessarily know all the windows, but hold on. That's like the pretty version. Kind of. To be honest, that's only half the graph. Did anybody get the whole graph? That's only half the graph. Okay, so some of you might have figured out there's more to this graph than just this. Zoom Standard only shows you actually half the graph. But hold on. Let me show you how I messed everything up. Guys, if you noticed, the variable is now a theta, right? Theta, angles, sines, cosines. Okay. I'm in radian mode. Hold on. I'm in radian mode. Which means when I do Zoom Standard, it's like, oh, 0 to 2 pi with little baby steps of 0.1. Why? Because between 0 and 6.28, I need lots of steps, and 0.1 will give me lots of steps. Now, how did I mess up my window? I said, let me pretend like it's degrees in a radian mode and say, okay, even though I know this will graph most, if not all of it in 2 pi, I'm going to pretend like I thought it was degrees and put in 360. To get a lot of steps in 360, we would want to go by 5s, not 0.1s. 0.1s would take forever. So go by 5s. And that's how I got my craziness. Just a bunch of stars. It looks kind of cool, but it's very, very wrong. It looks kind of cool, but it's very, very wrong. What's it doing? Here's the idea. If I'm in radian mode right now, just to let you know what's going on behind the scenes, if I'm in radian mode right now, usually sines and cosines finish one full cycle in 0 to 2 pi in radians, right? 0 to 2 pi, one full cycle, radians. 2 pi is 6.28. Guys, what steps am I taking? I'm taking steps of 5, right? So if I'm taking steps of 5, I'm going 5, and I'm ignoring all the stuff that just happened in radians, almost all of the 0 to 2 pi. And then take another step of 5, and I'm going some random place in the second cycle, somewhere between the 0 to 4 pi. Then I'm doing another, so I'm grabbing like 1 point from here, 1 point from there, 1 point from here. I'm picking all these random points in my calculator. My poor calculator is like, okay, I'll find the weird points that you want and I'll connect them, but it's not going to look pretty. In radians, what we want, and why Zoom Standard does it this way, what we want is to get lots of points in the cycles that I'm going in. So 0 to 2 pi, I don't want to like step over all of 2 pi. I want to make a lot of little steps in between and see what's going on. Hi, ma'am. Now, the problem is 2 pi was not enough, and I did that on purpose. On this one, the period is longer than 2 pi. It's been, in a sense, stretched, and so I think you'd want to go to 4 pi instead. Let's see if we can get the entire flower now. So we have 1 petal, 2 petals, 3 petals, 4 petals, 5 petals, 6 petals. Now, polar's kind of cool. There's a lot of cool stuff that you guys can do in it, and we'll see more as we go along. But hopefully you guys kind of realize what's going on with this theta min, theta max, theta step sort of thing. I gave you a really weird one. Almost always 0 to 2 pi is enough. Almost always Zoom Standard is a good place to graph. I just gave you a weird one where it's like, it only looks like it's kind of partially there. Polar curves usually have symmetry. And so if you don't, I see symmetry this way, but it's not a very nice flower centered around the origin. That's why I went to my window and made it a little bit wider. But just be careful with the theta mins, theta max, theta steps. If anything gets all like weird and pointed and what's that thing called where you can spiral graph or something like when you're a kid you can, did anybody ever play with those? Anyway, hi you. If it looks all like pointed and weird, your window's probably messed up. So do Zoom Standard and start all over again. Okay? With that, let's just talk about polar, because that's the calculator. There's all sorts of stuff that you can do. That's the calculator, though. Let's do by hand. Here's a big thing that's going to change in polar. Here's a big thing that's going to change in polar. Now, guys, don't worry about the circle-y thing. I'm going to actually have some like runoff ones for you tomorrow, like the unit circles that you can like paste in your notes. Although we're going to hopefully make it to where you don't need that circle-y graph. It's called a polar graph. You don't need it to graph. Don't worry about drawing this right here, but I do want you guys to draw what's going on up here at the top, just as we end class today. Do you see how the ordered pair is a little different than normal? Every ordered pair that we've seen this year has had an X and a Y, even in parametric, has had an X and a Y. Now we have an R and a theta. Looking at this polar graph down below, what do you think R is going to stand for? Radius. Good. Now over there on the picture it says directed distance, and that's true, but you can think of it as a radius, because all of these are concentric circles, circles within circles within circles, and each of them are going to have radii, actual lengths. So R is going to be radius. Theta is going to be, well, angle. I guess you could think of it as inclination. No, keep that with lines. Just think of it as theta. You could be in radians or you could be in degrees, but your zoom standard will change your window like we just saw. And guys, if we have these r's and thetas, here's something else that's kind of weird. In polar, we're going to be looking at, or we're going to be having functions that are r equals f of theta. Why is this weird? Isn't this usually the y? Doesn't the y usually go second? Huh, the order's kind of weird too. Tomorrow we'll figure out how to graph polar points, and also Monday, and also go over parametric equations. Have that homework started for me. And I'll see you guys later. My hoodie people, why are you so cold? Bye.